So what I started with first now is a set of questions here. So they are also on the hand-in problem set. They're sort of problems that are true and false. So these are a bit typical. And this idea of these problems is that you need to write 3, 4, 5 lines to show that something is true or false maximum. Or it might be something that you know from before. The problems that are in the hand-in problem set, I think, are slightly easier than these. Okay? These are probably a little bit more difficult because it's hard to solve these problems if you've never seen them be solved before. The other ones are more about your understanding of topics. And if you use lecture notes and you use what we've gone through, then you should be able to solve those. Okay, so let's start with this one. And let me start to analyze the question first. Okay, so it asks us whether this galaxy cluster has reached time of turnaround, which is the time when it stops expanding, earlier or after the time when the Milky Way virialized. Okay. So the first thing when you read a question like that is that it uses the terminology from spherical collapse. Okay, that's the first thing you see. Turnaround, virialization. That means, spherical collapse model. So that's what we have to do first. Okay, so then if I now go to the spherical collapse model, let's see if I actually can do this now. To get the right one. Here. Okay, so this was what we had from the spherical collapse model. You see, had turnaround and collapse. And it told us how the exact solution related to linear theory. So now you can see immediately these are the things we need to keep in mind. Okay, so the first thing then is that you will write down what happened at those times. So it says it has, and the other thing it says, this is one of those things which you haven't seen, it is a bit confusing. It says similar significance, and that is the same as the number of sigma, which is what we introduced yesterday. So that means that at the collapse, what we said is that delta C of Z is nu times sigma of M. Okay, that's what we wrote down yesterday as saying this is the significance of this peak. So now I can go back and I can use this situation. So now let me write it down first for the Milky Way. The Milky Way, okay, it talks about virialization. So virialization in this case is 1.69 times 1 plus Z, that's this bit, equal nu mass of the Milky Way. Okay, that's just writing down the first part of the question. So the Milky Way is collapsed. Collapse means delta of 1.69 times 1 plus Z. And then you can do the same thing now, and I'll probably put Z Milky Way here just to be clear. Then now I'll do the same thing for Virgo. But now it says turnaround. So Virgo. Then it's 1.067 is 1 plus Z. Virgo equals nu sigma m Virgo. Okay, so now I wrote the same thing down both for turnaround and for collapse. And now the question is Z Virgo larger or smaller than Z Milky Way? That's what we want to know. And so to do that, I don't know what this is, this nu, but I just know it's the same for both. So then I can divide. And I get 1.69 divided by 1.067, 1 plus okay, let's see. Hopefully it won't go on for too long. Hello. So now, the next step now is to agree how do we calculate this. And it's not so bad because we know how to calculate this sigma. Right? We have done that before. And we know that sigma of m is m n plus 3 divided by 6. I know the mass of both of these. I've been given that number. So now I can go one step further. And I want 1 plus Z Milky Way, 1 plus Z Virgo. It's 1.067, 1.69 times. And here it's M Milky Way, M Virgo, minus n plus 3 divided by 6. Okay. So this is now the solution. And now it depends on what this n is. So often these questions are a little bit open so that you're allowed to make your own, to realize that you need to make an assumption. Right? I haven't here written n. So now, but if I put in, I can then say, okay, well, on galaxy scales, n should be minus 2.35. Okay, let's do that. And if that's the case, and now I need to look up the number, then this ratio is 1.04. So if that holds, okay, if that holds, it means that Z Milky Way is larger than Z Virgo, right? By a little bit, 4%. So in this case, I would answer true on this problem. Now, I have made several approximations here. And I've done one thing that when I gave this as an exam question, nobody ever noticed, but which is still a little bit of an issue. I used the same n, even though the masses of these two are different by a factor of 400. And if you think about it, the real, and that's fine if your power spectrum is the kind of simple power spectrum we have considered, but the true power spectrum actually has curvature, right? It's not a single power law. So it's minus 2.35 here, but at larger masses, it might be slightly smaller, slightly larger, sorry, less negative, so minus 2. So what you could do was that you could do the same thing. You could say, okay, well, I don't know exactly what the n is for these two, but I will try with two different values. And you might get the same result, or you might get the opposite. Okay? It's very close to 1 here. So depending on the assumptions you make, your answer might be true or it might be false. Both answers would be correct if you justified it. Right? If you made a good reason why it should be like that, then the answer could be true or false. Both would be possible. So these problems don't always have a completely certain yes or no. Okay? Depends, because not everything is specified. There's often something that you need to make a decision on yourself. And when you change that decision, your result will change a little bit. But this will be the sort of standard way of solving it. And really the trick here is really whenever somebody talks to you, and this has nothing to do with problem set. It's just if somebody asks you, oh, I got this galaxy, I want to estimate when it formed. Okay? When it formed, well, then you think, okay, I'm going to then use spherical collapse model. That's visualization, formation, those kind of words immediately leads you to think about spherical collapse, and you use that. So that's how you read this. If it's a problem set, again, it's the same thing. You see visualized, or you see turn around. As soon as those two words are there, it means, spherical collapse model. It's almost always a complete identity between those. So that immediately gets us then to the second problem, where it also says collapse. So I'm going to remove all except this one. So now it says collapse again. And collapse, I said earlier, that's the sort of thing you should remember when somebody talks to you about collapse. So here it's actually possible, based on simple thinking about how the universe works, it's possible to answer this one without doing any calculation. But it's easier to answer it if you do the calculation. But the simplest way of thinking about it, well, you have to be a little bit more careful. But what we showed earlier in the course is that the universe is hierarchical. So things form, more massive structures form later. And at the same time, that means that the typical mass of a given redshift is smaller at higher redshift, right? It's the same idea, okay? The more massive things form later, hence the typical average mass that forms at a given redshift is lower at higher redshift. So this must be false. Okay? You can argue this is false without doing any calculation. But if you want to calculate it, and it's probably best, because it's easy to get it wrong if you don't, in that case, what you write down is that you say, okay, from the problem, we had this equation. Okay, that's what the problem means. Or you can now convert that. That's equivalent, in our case, to sigma of m equal to 1.69. That's that spherical collapse thing again, times 1 plus z. Okay, I'm just move this one over on the other side of the equation. So that's what this question says. Right? This is a 2 sigma fluctuation, and the question is, if I write this now down for redshift 1 and redshift 0, what's the masses? Okay, so let me just do that. Redshift equal to 0, or what's it? Let me just check what around. Then I call this mass m0. Redshift 1, I call it m1. And then you see immediately the only thing that comes in here is redshift. Okay? So sigma of M0 has to be, which is equal to 1.69 divided by 2, is less than sigma of M1, which is 1.69 divided by 2 times 2. Okay, that's obvious. Obviously, that's true. So now I have an equation, I have an inequality here. And now you remember what sigma is again. So this is then equivalent to M0 less M1 divided by 6. Again, I have made the assumption that the slope of the power spectrum is the same at those two redshifts. Maybe that's not quite true. Okay? So you get a smiley from me in my markup if you point that out to me when you're answering the problem, but you're not going to get extra points. You have to make an assumption that allows you to solve the problem. Okay? And that assumption will be it's the same. Okay? And if that's the case, then this here, if n is greater than -3, and that's going to be the difference here, of course. It depends on the sign of the exponent. So if n is greater than -3, this means that M0 is greater than M1. Right? Because your exponent is negative, you flip around the inequality sign. Okay? So in this case, yes, it's true. It's false. The statement there is false because structures forming at redshift 0 are more massive than the similar type structure forming at redshift 1. And that would be true at all redshifts. But here you can see the difference. If I now had in neutrinos, you remember this one power spectrum I showed you where the slope was very, very sharp, okay, cut off. In that case, n is actually much less than -3. And in that kind of universe, M1 would have been bigger than M0. So in that case, if n is less than -3, then the universe is anti-hierarchical. The first structures to form are big, and then they break up into smaller. And for quite a few decades, we didn't know what was the right solution for the universe. Now we know this is the right solution. But you know, if we'd done this course 20 years ago, we wouldn't know. Well, 90% would know, and 10% would be arguing for the opposite view. So these two are quite common things, and they are quite useful because they give us a way to estimate when galaxies form. Okay? And the first thing is that we typically say, okay, the structures will be 2, 3 sigma, and then you can use this kind of approach to give us an estimate on when they formed, if you know how big they are. The last problem is quite different. And it is certainly the easiest problem, because everything is actually there, except for one thing, and that's you have to calculate the binding energy. So let me just decipher the problem. The first thing it says is that the black hole mass is proportional to the bulge mass. Okay, I'll start with this one. That's stated explicitly in the problem. So this is M sigma, yeah. And well, actually, it isn't M sigma because then it would be the velocity dispersion of the bulge, which might not be directly proportional to the bulge mass, but it's one that's almost the same as M sigma. They're both used. People don't agree on which one is the best, but they tend to be quite equivalent. So if that's the case, I mean, now we're going to consider a situation where the fraction of mass in a bulge increases proportionally to the total mass. So then you write down the fraction of mass. That's the mass of the bulge divided by the total. And that's proportional to m total. That's the second statement in there. And then the first statement says that the energy output is proportional to m black hole. Okay, so the first thing we want to do now is we want to now express this in terms of the total mass. So m black hole is now proportional to m bulge. But this is proportional to m tot squared, right? And that also means that the energy of the AGN is proportional to the total mass squared. So not to the mass, but to the total mass. It's proportional to the bulge mass, but not to the total mass. Now, next thing is the binding energy. So let's see exactly what I wrote there. Okay, so let me write down what the binding energy is. So the binding energy of a gravitating sphere of some sort is proportional to gm tot squared over r. So that here you might be a bit stuck, because it might not be obvious what these things are. But we already looked at some of these things, and if anything, this radius should be proportional to the mass to 1/3, right? At least if the density is constant and there's no complexities in here, because the mass is the volume times the average density. So this has to be true, right? The radius has to go as the mass to 1/3. And that means that the binding energy will go as mass to the 5/3 power. Right? And then you can now calculate how the energies are. Take the AGN energy divided by the binding energy, and it's proportional to m tot squared over m, oh, sorry, it's missing tot here, 5/3, which is proportional to total mass to 1/3. So in this situation, the feedback process in a galaxy, if this thing holds, and it's not a crazy idea actually, it seems to very often be true, then the AGNs become more and more important the bigger the galaxies are. And that's nice, because that's what you would like to have to get feedback to explain the difference between the galaxy luminosity function or galaxy mass function and the dark matter mass function. Oh, that's something else. So is this clear? Mostly? Because I'm going to leave the analytic feedback off, and I'm going to go back to what we ended on in the noise yesterday. The simulation. I'm going to start out by one slide that I jumped over, because it was so noisy I couldn't possibly explain it to you. So let me do it now. So this is from this simulation, illustrious simulation, that I talked about earlier. Let me just remind you, it's this simulation here with the very large 18 billion particle simulation. And here's an example, and the reason why I wanted to show this is very typical now of what simulations give us, and why this is very useful. Now here is a dark matter density map of this region. That's what you'll see in the movie again. This is the optical image of this galaxy. This is what you would compare against images that you take of the sky. This is an example of a galaxy outside here. Now that immediately tells you one thing, which is something we're not going to do in the work here because it doesn't lend itself to analytic work, but that is that there is something called a morphology density relation. Galaxies that are in high density regions, and you see this is a high density region, tend to look like that, look like ellipticals. And galaxies out here, which is a low density region, tend to be more often disks or spiral galaxies. And part of the reason is that because you have high density regions, the chances of colliding is higher. And when you collide two galaxies like this spiral galaxy, you tend to get an elliptical galaxy. So part of the reason is that at least. The other thing people very often do is they create images of their simulation in other wavebands, because this only tells a small piece of the story. That's just the stars. That's what our eyes see. But as you see in the movies, this is only a very small fraction of what's happening. So this is often what they also produce. They produce a map of metals. So that's where there are heavy elements. And that's very useful because that's something we can measure relatively easily. And they show you this thing. Is something called Sunyaev-Zeldovich effect. This is when you have hot gas and you interact with photons, typically from the cosmic microwave background. And what happens here is that the photons in the cosmic microwave background gain energy from the hot electrons in here, and you will see a change in the temperature of the sky. So we can use this to map out what's inside these galaxies. And finally, they typically do it in X-rays, because we often observe these objects in X-rays. And this is this hot gas that we talked about yesterday in the cooling question. This is so hot that the cooling time for this gas is going to be very long, and it will just hang around as being hot X-ray gas. In addition, people very often give you things like the gas density. Where is there gas in this? What's the temperature? Again, temperature tend to be high in the dense, more massive regions, precisely because the virial temperature is higher in a high mass dark matter halo. So it's precisely what we've seen. You can see it's, if you look at this scale, these don't look too far away from being spherical, right? And that's because at some level, dark matter halos are actually quite reasonably close to spherical. They're not completely, because they have some slight rotation, but they are not so far away from spherical, and that's why you have these fairly round clumps here of high temperature. You can use this to find out where the dark matter halos are if you compare to this. Well, if you compare to this, you already know. Here you already know where the dark matter halos are, but you can anyway look and compare these two. Entropy, of course, tells you where there's been energy injected. That's also a very popular thing to look for together with velocities. So let me just show you, go through this one movie again, which I think was the one we stopped at yesterday. I don't know, can we turn off the light again here? Is that possible? Because then maybe that's easier to see. Super. Okay. So this is at the early stages of the universe, and you mostly see here dark matter. You don't see much effect in terms of gas. If you're really close to it, you can see some things here. Okay, that's because early on, only small dark matter halos exist. Relatively small objects will form. So most objects at high redshift are going to be small. A few are going to be big, and they're going to be the sort of exciting pieces. The main action in the universe, we know from the star formation history of the universe, is around redshift of 2. And that's going to be, you're going to see that starting now. It's about right now. And now you can see the explosions, the high temperature gas being ejected from feedback. And this is how feedback really looks in a simulation. I have no idea if that's what it looks like in reality. But in general, you get these big bubbles of gas that sometimes clearly escape its dark matter halo. You can see that sometimes the dark matter is still in blue here. They don't indicate the gravitational limits, but some of these bubbles surely go outside the virial radius of the dark matter halo. And what they do means, which I didn't talk about yesterday, is that they drag along metals, and those metals will then end up in what we call the intergalactic medium, which is the medium between galaxies, where no galaxies have really formed. And it enriches that medium, and it has then that becomes higher metallicity, and in the future it will be easier to form structures in there because the cooling will be more efficient. So these movies, they only create in order to show off more than anything else. You rarely use these movies to do science. They're not useful for science as such. They might be useful to get insight. So looking at these movies are not a bad idea. It's like you look at them and you get a feeling for what happens. And then you might try to summarize that in some simple equations. But in truth, what they usually do with this is they have to compare the outputs to observations. I'm going to show another movie in a second, so we can turn it on then. So here's one example of this from this paper. What they did here was they looked as a function of distance from the central galaxy in a dark matter halo. You look at how many satellite galaxies there are. Remember this thing that you have galaxies that fall into a bigger halo, and they become satellites of the central galaxy. And here they then compare observational data. Oh no, sorry, the observational data is the green line here, to their predicted halo functions. And the agreement is relatively good. They did the same thing for mass and gas content, amount of gas in them. The red line here is observational data, and this sort of spread here is a set of their simulations. So that you would consider good agreement. They also compared against the metallicity in stars, the mass of the galaxy, and typical average metallicity of stars. And this is the observational data, the green points, and the histogram in the background, the simulations. This is what it usually looks like when simulators do this calculation, and I still don't know why. There's quite a lot of difference here, and I don't know why. But usually they say it's good, so it must be good. Okay, I'm going to skip over that one. And they tried to do the star formation history of the universe, and these pink points here, plus these points here, which are high redshift, and these are all lower limits. They must be higher. This is what they observe, but they know they only observe a little part of the universe, so they must be higher. The black line is the total star formation history in their simulation. And you must say that's a pretty good agreement with observations, but they produce too many stars at late time. Okay? The observations go down, they stay around. So they might need more feedback. Okay? And that goes a little bit back to that movie, because you see in that movie the feedback stops being very efficient. There's not so many explosions at the later stage. So this is one of the two groups that have done simulations. I would say it's hard for me, as in, not somebody who does this kind of stuff for a living, to say which ones is better. But this is the other simulation. This is called the Eagle simulation. It's run by the Virgo Consortium. It's led by Joop Shea in Leiden. And they focused more on scientific plots and less on their fancy movies. But here's an example around a spiral galaxy. And you can see you're tipping it around, and you see when it comes edge on, you can see dust lanes here. So there's some dust in the outside of these galaxies. So this looks very, very similar to what you would call a flocculent spiral. A flocculent spiral is a spiral where the spiral arms are not very well defined. There's an arm here, there's an arm here, there's an arm here, but you don't see them very clearly. Okay? Those are called flocculent spirals, and they're very common. And this one looks very much like one of those. The actual universe simulation they have is this one. This one starts a higher redshift than the other one. So at redshift 20, so redshift 20, the universe was very uniform. This shows you cold dark matter. Let's move it forwards in time. It's now rotating. The universe is rotating for us, or we are going around it. And you can see how structure is forming. Okay? Now we're at redshift 9. And you can see this is a lot more defined, a lot more clumps than we had earlier. And so let me go back, because there's one point I wanted to make before the zoom in really starts. Come on. Okay. Ay. Clumsy. Okay. So this is redshift 20. And if I go to redshift 5, how much do you think these overdensities will have grown? Now, if you remember what we have been doing in terms of growth of perturbations, we said that overdensity, delta, is proportional to A, right? And A is, of course, proportional to 1 over 1 plus Z, right? So now you can calculate what that ratio of delta at redshift 20 and delta at redshift 5 is. And it's going to be close to 20 divided by 5, right? So it's not quite, but it's about a factor of 4. So but then if I now let it run, no? Okay. I'm now going to run it until redshift 5. I hope that's before the zoom starts. Okay. Stopped it just too late. I'm just going to move back a little bit. Okay. It's almost 5. Does this look to you as if this is 5 times more concentrated? Well, here's the problem with looking at a movie. It's almost impossible to say, right? I mean, there's no way that your eye is going to say whether this is 5 times more concentrated or 10 times more concentrated. There's no chance, right? But at some point, this argument here, this only holds when delta is much less than 1, right? It's only in the linear regime. So on large scales, this is probably true. But here, where you see these black knots, these systems are no longer linear. When you see them as a black thing in this movie, it will be a nonlinear structure. So it will have a much higher overdensity than you would get from this linear extrapolation, because gravitational collapse really has happened. So now I'm going to continue it. Now they're going to zoom in on an interesting structure. And now notice now how many mergers there are, how many times galaxies collide with each other. And it's going to change to gas density instead of dark matter. So here you will see. Look at how they clumps all come together, colliding constantly. And now we have a spiral galaxy. This is redshift 1.4. We're going to move on up to redshift 1. And what you're going to see here is there's going to come other structures are going to come in. And look at this disk. Now it has nice spiral arms, right? Most of you will I agree with that. And it's going to stop at 0. There we go. And that's this flocculent spiral galaxy. And this is what you would call a quiet history. Okay? This is not, now we switch back to cold dark matter again. This is a very quiet evolution for a galaxy. If this galaxy had had a violent evolution, it would, at the end, it will look like an elliptical galaxy. But you can also see that all these collisions, they destroy disks. So if we go back again, at this point, I don't think you would say that this thing has anything very particular. It's not a disk, it's nothing, it's just a bunch of chaos, really. But all these particles typically come in after this point. They typically come in more or less on a plane, or more or less with a similar angular momentum, similar direction of their angular momentum. See, typically you get a lot of things that come in here. A few things come from distance, and eventually they build up this disk here. And the funny thing is, when we calculate, estimate properties of that, which we're going to do now immediately after this, we're going to assume that these spiral galaxies are isolated. Right? And looking at a movie like this, that makes you wonder whether that assumption is a good one. And that is something that you should always keep in mind, but we're going to ignore it. So. This used to be the most difficult thing to do in galaxy formation simulations, by the way. Only in the last 5 years or so have people been able to properly simulate disk galaxies that look real. There was always a problem, in part numerical, that made these galaxies be too small. Now they have the right size that you can compare them to reality. Okay, now I'm going to stop with the movies for a while. So I guess we can turn on the light again. So that was the movie time. I'm going to move to disk galaxies, because remember, one of the things I wanted to explain in this course was why disk galaxies have the size they have. And just to remind you, it is really very striking. There are two things that are very remarkable about spiral galaxies. One is that they typically have an exponential light profile. So their light, their surface brightness goes down as e to the minus r over h, where h is a scale radius in this case. And it's also dominated by rotation. And that makes it different from elliptical galaxies. Elliptical galaxies are not dominated by rotation. The majority of their dynamical support is due to random motion of stars. Now, this is just kind of like a definition. I'm not going to try to show why they have that. They kind of disk galaxies when they have this, so I'm not going to look at that. It would have been nice to explain to you in a simple way why these galaxies have exponential light profiles. And I'm not the only, yeah, sorry.
Before you explain that, for elliptical galaxies, you say that they are dominated by random velocities and such, but do they have an angular momentum different from zero?
So usually, they have a tiny bit, but a very small amount. So usually what so it's usually defined in terms of the, well, it's usually defined in terms of the tensor-virial theorem. And the tensor-virial theorem basically has one support which is rotational, and one which has, so that's VI. And then there's a term, pressure term, which is a depends on velocities in different directions. And that's basically dispersion, velocity dispersion in the galaxy. So you typically have a contribution of rotation, velocity dispersion, and gravitational potential. Those are the three terms that come into it. And for elliptical galaxies, basically that rotation term is very small relative to the others. Doesn't have to be zero, and actually quite a lot of elliptical galaxies have a small disk in the center. So they have some population, and basically they are gathering all kinds of orbits. Some that are rotational, some that are chaotic, some that have other distributions. But there is a little bit of angular momentum in ellipticals, but it's very little. So, and it's mostly because it's cancelled from all kinds of. You get motions in all kinds of directions, and effectively that will cancel out some of the rotation. But there are several families of elliptical galaxies, and in some of them rotation is more important than others. So it's not a very trivial thing to answer as like a. But in all cases, elliptical galaxies that we know of have rotational support, which is much less important than anything else. So that's the right answer. That would be the truth. Okay. So the other thing is the exponential distribution. Well, firstly, so this comes now back to the rotation. To be precise about this, spirals don't have exactly exponential distributions. They change, they differ a little bit. And an exponential distribution would basically be a case where if you have intensity as a function of radius, you would have a distribution that looks like this. I'm not sure whether that's an exponential. That almost looks like it's going to hit zero, but okay. Okay. So that's what an exponential one looks like. A real spiral galaxy, most spiral galaxies, like take the Milky Way, which is a spiral galaxy, it would have a distribution that went much sharper up, and then perhaps it drops off like a spiral galaxy. And so in this case, I spiral is I disk plus I bulge. So these have a central bulge, and the distribution of light in a bulge is different from this exponential. So a real spiral galaxy typically has two components, and it's only the disk, the outer disk, that's described in this sense. I'm going to ignore that, okay, because the bulge is important, but it adds complications, and I don't want to try to explain that now. But the bulge then provides light in the very center, and so that can always change the central profile a bit. Many spiral galaxies also have some deviation from this profile at very large radii, and that's less well understood. So, but we're going to ignore that, and over a large range in radius, particularly for low mass spiral galaxies, this is very close to be universal. So then you would, of course, like, when you see something that's universal, like this galaxy looks like that galaxy looks like that, you ask why. Right? That immediately is an indication that there should be some interesting physics that explains why it's like that. And nobody really knows. Okay? There are a few models that explain why light profiles are exponential, but there are none that are really satisfying. So we don't fully know why it's exponential. So we have to, again, accept that. It's the same thing with the Navarro-Frank-White profile. Again, I said all dark matter halos have the same profile. That hints that there is something fundamentally gravitation that leads to that profile. It should be an attractor of the gravitational system. Again, well, there are quite a lot of papers that have been written about this. It does not seem to be, there certainly doesn't seem to be a simple explanation. I'm not sure there is an explanation that there's consensus about. But there ought to be something that's clear and reason why it's like that. And the same thing with this exponential profile. When something is universal in nature, there should be some reason why it always converges to that solution. So it's interesting to get a better answer on this. There are ways you can easily make exponential distributions. So viscosity, for instance, will help you make exponential distributions very easily, but they don't work from the initial conditions that the universe has. So, it's a bit of an unsolved problem. Okay, but to start with that, we need something to deal with our angular momentum. Angular momentum is essential for disks because that defines them. So we're going to introduce something called the angular momentum parameter, lambda. And to get a feeling for what that means, let me just write down, this is the angular momentum of a simple system where I have a small particle moving around the distance of r from its rotational center on this velocity in a circular orbit. The circular velocity is given by this expression. Okay? Those are the two basic things. But now, so you can combine those two, and you get an estimate of the circular angular momentum in terms of useful variables, like the mass and the radius and a constant. Okay, so that's straightforward. But most things in the universe are not moving on circular orbits. Just this is easy to calculate. So you would like to live with that. So what we define then, instead, is we define this lambda parameter, which is then the angular momentum, the actual angular momentum, divided by the circular angular momentum. So this is the actual. So what you can see is that this will have a maximum of 1. So it's on 1 if everything moves in circular orbit, on one circular orbit, then it's 1. It will be very small when there is very little angular momentum in the system. And typically, for spiral galaxies, this is of the order of 30%. 0.3 to 0.5, something like that. So you can calculate it. You can write it out. Lambda is J over the mass to 3/2 R 1/2 G to 1/2. But we don't usually write it in that form. We change the units a bit, and we introduce the energy, the binding energy of the system, which is gm squared over r. And if you put that in here, you'll find this expression for lambda. And this is the form you usually will see it in. And it's the black one. I'm going to write it on two places because it's such an important parameter. So lambda is equal to J, binding energy of the system, and G m to 5/2. Okay. So a bit annoying with all these square roots and stuff, but they are not so hard to deal with in reality. So this angular momentum parameter is actually defined like this. So if you get an n-body simulation from somebody, a theoretical calculation, you would not use this as your definition. You would use this as your definition for the angular momentum parameter. Okay? You would calculate the binding energy of your particles, and then in their mass, measure their angular momentum, and get the angular momentum parameter. So now we kind of disconnected this and this. For this simple scenario, these two are equivalent, but this is the definition that you should use. Often you go back again because this is a convenient way of writing it, but this defines lambda. And this is the quantity that we use to talk about angular momentum in cosmology, always. And so people have, of course, then measured this a lot. it's one of the standard things you do if you have run an n-body simulation, is you try to calculate what's the angular momentum. And what people found is quite interesting. They find that the likelihood of lambda, it's this black line here, the likelihood of lambda as a function of lambda has this form. It's what's called a log normal form. So it's like a normal, like a Gaussian function, but now with the argument ln x rather than x. Okay? And so that's what they say. That's the distribution of angular momentum in dark matter halos. And you can see this is pretty universal. Okay? If I ran a model, an n-body model tomorrow, I would get a distribution like this. If one of you ran an n-body model next week, you would get something like this. And the distribution, the parameters are around that value. We would get something close to that. I mean, you wouldn't get exactly 0.5 and exactly 0.035, but you would get something that's not very far away. And so there's two things you should notice here then. The red line here gives the cumulative likelihood of a value. It basically says what's the chance of lambda being less than this value. And that's the red curve. And so it says that being less than 0.01, well, the likelihood is small. It's about 2% or something like that. Whereas the chance of it being less than 0.1 is 99.8%. So this spin parameter is typically between 0.01 and 0.1. Not very much scattered. So then you might ask, now given what I said earlier, well, this is universal, there must be some universal explanation for why it looks like that. Right? That's very reasonable. And in this case, people have worked it out. It is a little bit work to go through it properly. But basically, the reason why dark matter halos spin is due to tidal forces. And so that's basically because you have these big clumps and they fill up large part of space early on when they're still in the linear regime or almost a linear regime. And then torque from one clump here on another clump here will lead to slight increase in angular momentum. So this is set completely in terms of tidal forces. It's a funny history behind this, because this was worked out. People realized this not for dark matter, because dark matter wasn't thought of, but for baryons, it's the same thing, already in the late 60s. So there were papers written in 1967, 68 that worked out this what the typical angular momentum of a primordial halo would be. And they turned out to work fairly well for this. But it turned out, and then there was a Russian called Doroshkevich who also did it in 1970, and he got a slightly different result, but he also had a tendency to write papers that were so unreadable that nobody understood them, which is always a bad idea. So for a long time he was ignored, but he actually had the right solution. And it was only until Simon White in 1984, 83, 84, he worked this out properly, that he realized that all these earlier results that everybody had been using since the 60s, they were all wrong. They all got it wrong by some important factor. So he did a proper calculation of this, and he showed what the typical value is. So he showed typically what this number is. It's that it is a log normal distribution. I'm not sure follows directly from his calculation, but he shows that it is very generic. So that is essentially independent of cosmology, this mean value, and it's just set on.
Sorry,
yeah.
Where do you find that value?
So this value is something that you just measure out of n-body simulations. So you calculate you just identify dark matter halos, and you calculate what's their spin parameter. And then you just tabulate it, and you get a distribution that's like this. So you fit it. Yeah. And it's very much, it is completely set by tidal torques. So the theory exists for this, and it is indeed universal. But this is where spirals lie. Okay? So spirals between 0.3 and point, yep.
And where are blue
Good question. They are in here. They are a little bit higher than the dark matter halos, but not, but entirely consistent. The little we know about it. I mean, this is not easy to calculate, but they are in that regime. They're small. They're entirely consistent with having the same angular momentum as their dark matter halos. So. But yeah, that's a good point. I never thought about showing that here. So the spirals are much higher, and you can see they are totally inconsistent to the distribution of dark matter halos. So that means their angular momentum cannot or doesn't seem to be related to the dark matter halos. So how do you spin things up? Well, you spin things up very logically. You spin them up because they get smaller, they collapse, right? So that increases their angular momentum because the radius becomes smaller. So if you go from an initial radius here to final radius, you need to calculate what your angular momentum parameter is. And you can do that fairly easily because this parameter will change because your radius will change. This will be constant. Your initial angular momentum is going to be constant, conservation of angular momentum, but your spin parameter is going to be proportional to J gm squared over r, 2.5 divided by gm to the 5/2. Okay, that's actually this. It's approximately equal sign here. It's approximately equal because there is some constant of order unity in front of this potential and binding energy. So this means the only thing here that changes as you change the radius, the mass stays constant, everything else stays constant, angular momentum is conserved. So what you get is that this is proportional only to r 1 over r, the square root of r. So the angular momentum parameter, the angular momentum is of course conserved. In this case there is no exchange of angular momentum with anything else, it's just one rotating structure that you just shrink, and conservation of angular momentum is, unless something takes the angular momentum from you, it has to be conserved. So J has to be conserved, mass is conserved, radius is not conserved. So then you can then calculate these different things. So you do R initial radius over the final radius is equal to the spin parameter minus 2, and that's, as it says there, about 200 for a spiral galaxy. So if your spiral galaxy lived in a normal dark matter halo, the normal dark matter halo starts with a spin parameter of 0.035, and the spiral, you want to get it to about 0.5. It means that it has to start at the radius about 200 times larger than the final radius. So that doesn't sound crazy. I mean, you don't have much of a feeling for it perhaps, but it doesn't sound completely nuts. But what is it? Okay. So let's assume, well, maybe I should go to the next slide so I don't remember exactly which numbers I put in. Okay. Right, so if you assume the Milky Way is about 10 kiloparsec in size, it's give or take not such a bad number, it means that the total size, where you're starting with, is 2 megaparsec. And here is one of those problems where megaparsecs and parsecs, it's just big numbers, you don't have a feel for it. So the logical thing is to say, at least let's ask how long will it take from our starting Milky Way, 2 megaparsec in size, to get down to 10 kiloparsec. That's just gravitational collapse, right? How long does it take for something to fall from 2 megaparsec to 10 kiloparsec? You can just calculate that. And just using free fall time, that is quite a long time. That's 10 times the age of the universe. Okay? So if this was, yeah?
That calculation is only with baryons. No?
That's only with baryons.
So why our initial should be the same as dark matter?
Ah, okay. Yes, I probably should make that. Yeah, that's right. I didn't say that explicitly. Okay, so what the distribution function I showed is for dark matter, but this value is only set by tidal torques, and tidal torques will be the same if it was baryons or dark matter. So in a universe where you start with only baryons, this would still be the right starting point. But yeah, that's a good point because I didn't actually say that earlier. But indeed, that's actually true even in a dark matter universe. Baryons start with a spin parameter of 0.35. They start with the same spin as the dark matter halo because they are affected by the same tidal torques. So you always have the same starting point. So yeah, indeed, this is completely useless. So you need something else. Okay, so you need dark matter. And in that case, your initial is again written in this form. Right? It's the same thing I wrote down here. But your final lambda is for a different subset of the halo. So here I measured everything in baryons, but now I'm going to do something else. I start out with a halo, not very bright, good, which has dark matter and baryons. And this has this value of the initial conditions, where here this is for baryons plus dark matter, and this is the same for both. And then the final stage, what we measure in a spiral galaxy, is from the baryons. We measure this from baryons because we can't easily do it with dark matter. And that is then the disk angular momentum, the angular momentum of the particles ending up in the disk, the binding energy of the disk only, and the mass of the disk in here. So see, now it's only the disk component that come into this angular momentum here. So now when you now combine that, you can do the same calculation, and what you find is this expression. Okay? That's just taking the ratio of these two here. And now you have two ingredients here. Well, it's just slightly slight rewriting. Maybe I'll go back from this one first because there's one point I wanted to make first. Okay, so now this first thing is that you have to focus on these two parameters here. So the angular momentum in the disk relative to the angular momentum in the dark matter. That might very well be of the order of unity, because you say they start with the same angular momentum. Unless there is a particular subset of the particles that end up in the disk, this is probably of the order of unity. This is the mass of disk relative to the total mass. That's probably going to be related to the baryon fraction of the universe, reasonably. So that leaves just calculating what the energies are. The energies are gm square over r, where you have either m dark matter or m disk, and you get this expression for the ratio of their energies. And I have absolutely no idea why. Oh yeah. Okay, let me write out what I did there, because I made one change which I didn't write down. So what I wrote was I wrote down that the energy of the disk is going to be md rd, and I've written down that the energy of the halo, or all, was k m over r. So that's what this ratio is. Okay, so this is just the energies of this. And so I just took the ratio of these two, and I got ED over E. It's approximately KD K MD M. Oops, sorry, it's a square missing. And R D over R to minus 1. Okay. So that's, but I see I didn't include the K anywhere. So that's just to calculate the ratio of binding energies. So this now will go in here. Okay, just put it in here to get rid of these E's. That's all we did. So now you can do the angular momentum. And this is something we will come back to again later. So if baryons collapse and don't exchange angular momentum with the dark matter, okay? Yeah?
Sorry, what is K?
Oh, so K is just, so K is just a structural constant. So depending on your density distribution, so when you calculate the binding energy, the gravitational binding energy, you do an integral over the density. And depending on the density, this will have a it will typically have this, you will almost always have this expression, gm squared divided by r, but it will be multiplied by some factor which depends on the mass distribution. So if you have a uniform sphere, then K is 3/5. Okay. So that's just what it is. You just take the integral over the density distribution, because the potential, that's what the binding energy of the halo is. And then you get different Ks depending on whether it's distributed like uniformly, whether it's the same density everywhere, whether it's an isothermal sphere, whether it's NFW profile, you get slightly different numbers. And I put it in here for no particular good reason, because the only thing it does is it obscures the argument. But since I had written it down on the slides, I thought I should just write the equations out in detail. So in principle here, it will be a bit different, because this one is approximately spherical with an isothermal density distribution. This is going to be flattened and not going to be very isothermal. So that's why it is. Okay, so now the argument in here is that if I go back to this one here, now we want to do something with the angular momentum. And if during the collapse there is no exchange of angular momentum between the baryons and the dark matter, then the angular momentum per mass is going to be conserved. Okay? Because each particle, each mass bit, is going to conserve its angular momentum. And so that means that J divided by MD, or JD divided by MD, or J divided by M is going to be constant. And if that's the case, then you can solve the equations on the previous page, and you get initial to final. It's going to be given by the same ratio that we had before, but now modified by one crucial ingredient, namely the fraction of disk from the total. Okay. And that's just because you calculated the spin parameter, but you're no longer taking all the dark matter in the entire halo into account. You only take into account the bit that ended up in the disk. And that helps quite a lot. It reduces our time of collapse from 100 billion years to 5 billion years. So in this simple scenario, it still is difficult to form big spirals very early in the universe. And actually, that is, although it didn't look like that, that's very similar to what you saw in the movie. The spiral disk in that movie was only ready, big spiral disk, by redshift 1.5. And that is about 5 billion years after the Big Bang. Okay? The process of gathering putting things together is chaotic. It's not a simple collapse down, but in order to get all the material you need to come into the center and create the spiral, it still needs to fall that far, right? Regardless of how it comes in, it doesn't matter. It's just a free fall time scale. It's going to set how long it takes to get that amount of mass inside a spiral galaxy. The process and how it comes in doesn't matter for this argument. This is just free fall time scale. And you couldn't make that spiral galaxy earlier because the material you needed for it was still falling into it. And that's what you saw in an earlier stage. Now, if you have a very dense environment, you might be able to do it slightly quicker. If you have a halo that is rotating a lot, it might be easier to create this at an earlier stage, etc. Because this lambda initial can vary by a factor of 10. Right? I gave it to be 0.035, but it could be, it's not unlikely to be 0.1. And then you shorten this by almost an order of magnitude. So factor of 3 squared, so a factor of 9. So depending on the initial conditions, you can form some things more quickly than this, but this is sort of the generic scenario. No. Oops.
Even this result is big, it's greater than we expect.
It is quite a long time, yeah. And that just means that in typical halos, big spiral galaxies just simply don't form very quickly. They need time to spin up everything and gather all the mass together. But there is flexibility because you can vary this.
Yeah. So you can change the parameters to get some only a few GHUs or something.
Yeah. So if you go out and you look at the sky and you find a spiral galaxy that's a big spiral galaxy like the Milky Way, and it's at redshift 4 or 5, 2 billion years after the Big Bang, then my bet is that that spiral galaxy has to live in a halo that has a higher spin parameter than average. Right? It has to be in a non-typical dark matter. That's the only way you can form that spiral at such a high redshift. But you can do it, it's just harder. And you have a smaller chance to find them. Yeah?
So with the dynamics of the pairs of the spiral, I can't say anything about dark matter.
Oh, you can, but that's a different argument. So yes, no. So here I've hidden it all the way, but of course you can still do, because if you and the way that you do it isn't on looking at this. What you do is instead you take your spiral galaxy here and you measure the velocity here, and that velocity is going to be proportional to the square root of gm over r. It's just a circular velocity. And so that tells you how quickly it should go. You know the radius, or you measure, so you measure this rotation velocity, you measure the radius, and that tells you how much mass there is inside. And then you can go out and you can count the number of stars, you can count the gas, you can measure the amount of gas, and you can measure how much baryonic matter there is inside your radius. And if that agrees with your mass estimate, then there is no dark matter inside it. But in most cases, particularly when you go far out in the galaxy, there will be a discrepancy between this mass and the mass that you actually measure inside, and that's dark matter. And that's dark matter, that can be baryonic matter. It could be baryonic matter that you can't see, like black holes, neutron stars that have cooled down, white dwarfs that have cooled down. Those are baryonic structures. But it could also be non-baryonic dark matter. Axions, supersymmetric particles, etc. It's not clear what it is. But you can do it, but you do it like that, in a dynamical sense. The spin parameter, no, it doesn't tell you anything about dark matter. The spin parameter in itself isn't, at least not in that formulation, not going to depend much on dark matter. Not going to give you any insight. In fact, you would want to do a slightly better job than this, because this is very approximate. This just basically gives you it's a time scale argument. And okay, I'd summarize it very much as a very short one, but I'm going to give you a slightly better model for spiral galaxies. Because what I wanted to get was the size right. So let me do that, and I'm going to do it here. It's summarized in few lines on the slides, but I'm not going to use that. It's too short. Okay. Now, let's make two assumptions. I need to make a couple of assumptions in order to make progress. So the first thing I'm going to do is just for my own convenience, because it's much easier. I'm going to assume that the density profile of the dark matter halo is an isothermal profile. So thermal. This is only for analytic convenience, okay? It's not a crazy approximation, but it's not good enough. But we'll come back to that later. If it's an isothermal profile, we have that rho bar is given by the circular velocity squared 4 pi g r squared. That's the isothermal profile. Then we also know, the other thing I'm going to assume is that we can ignore self-gravity. So that means that the disk, the gravity of the disk, will not affect the dark matter halo. Okay? So I can deal with the dark matter halo and deal with the disk independently of the dark matter halo. This is true if dark matter is 99% of the total mass in the universe, then this will be okay. As it happens, baryons make up something like 20% of the mass of the universe, so they shouldn't be ignored, but I'm going to do it. Okay? They have a slight effect and it's hard to justify. And finally, I'm going to use the collapse criterion. So I'm going to say that my object form, when the density within the virial radius, the mean density within the virial radius, is equal to omega matter delta C and the critical density. Okay? At Z. This is just as a reminder, is 3h of Z squared over 8 pi g. Okay, that's just well, this is not so much an assumption, it's like a definition. Defines the radius of the system. So then you can do this, we did this the other day, and you can redo it yourself, and you will find that, and I'm going to write my virial quantities in terms of the virial velocity rather than radius and mass. It's slightly convenient, more convenient. The radial velocity is then 2 omega m plus c vir to z. You can see that this is, when if you fill in and you approximate the Hubble constant as being given as h naught times the square root of omega m times 1 plus z to 3/2, you will find that this is exactly the same I had before. And the mass within this virial radius is 2 omega m delta c, the virial to the third power in g h of z. So I'm just using those. It's a slightly different way of writing them, but they're useful as we're keeping in mind. Okay, so now let's start. So first thing I'm going to do is I'm going to write the mass of the disk and relate it to the halo. I don't know exactly what it is going to be, but I'm just going to write that the mass of the disk is some fraction times the mass of the halo, m vir. There's nothing in there, really. Right? I should say that in the literature, this parameter in the literature is known as little m d. I don't use that myself because it's so hard when you write on the blackboard to make little m's look different from large m. And since this is large md, and if I have a little md here, it's very confusing and very easy to get it wrong. So I call it fd, but in the literature it's called md everywhere. Okay. So we can write this one down using this expression just to give get a feeling for what the sizes are. Okay, so this md is approximately, so this is, I just inserted numbers just to get a feeling for sizes. And okay, so that's a typical size of the disk for those parameters. And you can immediately see a couple of things, what's important and what's not. Okay. The dependence on cosmology on these parameters that define the collapse, that's quite low. It's a square root of the dependence. So this is not very sensitive to this. It is a bit sensitive to the Hubble constant. If you know what the Hubble constant is today, and we kind of do now, I think, a reasonable degree, then this is not so important again. It does depend on the fraction of mass that ends up in a disk. I put 5% of the total. That is uncertain. And the virial velocity, I use 200 because that's the kind of velocity that the Milky Way has. Now, let me see if I can find my slide. Somewhere I had this number for the Milky Way, but I don't have them anymore. Okay, too many small slides. Okay, so I'm not going to tell you what it is for the Milky Way, but you can fill in 220 kilometers a second in here, and you will get a value that's slightly bigger than this, slightly high. Okay, so now how are we going to make progress next then? Because we haven't really done anything profound yet. The only thing I've done is I define my disk mass in this form. Now what we need to do next is we need to assume that our disks are exponential. And that's crucial. Exponential disk. Okay, so I of r, well, actually, I'm going to make it explicit that this has surface densities by using sigma, which is what we usually use for surface densities. Sigma var, sigma naught e to the minus r over r d. Okay, that's the assumption that it's an exponential disk. Okay, if we have that, this is the surface mass density. I can now calculate the mass of this just by integrating it out to infinity. So the mass of this disk is integral. Now I have to change to polar coordinates, right? So I get an integral over from 0 to 2 pi and an integral over r sigma naught e to the minus r d r from 0 to infinity. So that's how you get the mass of this disk. And of course, this integral is not a difficult integral to do. And you get final result of 2 pi sigma naught r d squared. So that's nice. Now we have an expression for the mass of the disk, which we can relate to this. The next thing we need is the angular momentum of the disk. Now, the angular momentum of the disk, formally speaking, is an integral over all space over r vector, where r is the vector from the origin, from the center of the galaxy to your mass element, times the velocity, the circular velocity at that radius, integrated over all mass elements. Okay, that's the explicit bit here. Now you can write what that mass element is in a small bit of an angular bit. I'm sure you've done this before. And you get again this conversion to a polar integral from 0 to 2 pi, 0 to infinity. Now you have an r squared. That's that extra r from this little mass element that you need to take into account. E sigma naught E r d, and the velocity dr. Now this integral is easy to do for the isothermal sphere. And that's partially why I introduced it. In case of the isothermal sphere, the circular velocity is constant. It doesn't depend on radius. So that's very convenient. Basically, the mass and the radius decline in the same way or change in the same way. So for isothermal sphere, r is Vc constant. So that's very nice because I can now take it outside this integral. If not, if I didn't assume that, if I had say an NFW profile, then this is not constant with radius and you need to include it in the integral, and then it's not solvable in analytic form. If that's the case, then it's actually, oh sorry, I forgot one thing. This should be, say, JD, because I'm only doing the disk. Okay, I'm not doing the dark matter halo. So JD, sorry. And it means that the angular momentum is then going to be 2 pi sigma 0 times 2 RD cubed W, not W, VC. And now you can just go back and you can look at this one. Oh, 2 pi sigma 0 RD square. Okay, 2 pi sigma 0 RD square. Take a bit away here. That's the mass. So this angular momentum is 2 times the disk mass times the disk radius times the circular velocity. So now we're nice. Now we have an expression for the mass and the angular momentum And now you see where we're going. We're going towards the angular momentum parameter. But to get the angular momentum parameter, we need one more thing. And we need to relate this to the angular momentum of the halo. And so we write, let me see which one I wrote, yeah. We now, little jd is large jd over the angular momentum of the halo. So, just to be explicit about this, it's disk, and that's halo. Now this you don't really know what it is, okay? What I talked about earlier, this has been this thing, the angular momentum parameter, that we know what it is. That would be 0.5 divided by 0.035. But this you don't know, this is the angular momentum. The angular momentum of the halo could be higher than the angular momentum of the disk. That's a different issue. So we'll come back to that in a second, what that is. Hope I get that beforehand. So now we can go back and write down our angular momentum parameter. G m vir to 5/2. Okay, that's the angular momentum parameter of the halo. And this thing, by adding in this and this and no, this and this only, that's the two things you need. And this becomes 2 md rd circular velocity energy to 1/2 divided by this small jd, this one, gm there to 5/2. So I just inserted this one here, the only thing I've done. And this now, I can now invert this and I can get an expression for the disk radius. That's what we remember, that's what I want to get, right? I want to get some size estimate of the size of the galaxy. Now solve this now, we get the disk scale length. The disk scale length is going to be RD, I'm not doing anything except just solving for RD, is equal to gm virial mass 5/2 to velocity, we call it virial velocity. I changed my velocity to v vir because, as I said that's what I used earlier in the equations, and for an isothermal sphere, this is constant, whatever I call it. This is JD, this is FD, and I got something wrong here. Say 3/2. So what I used in here now is I used MD is FD times M vir. So I just use that in here to get rid of MD, M disk. And the convenient way of doing that is I don't know what the ratio here is. I don't know what the ratio MD to M vir is. I don't know those two numbers. But this ratio, if angular momentum per particle is conserved, then this ratio is 1. Because this basically is the angular momentum of the halo divided by the mass of the halo divided by the angular momentum of the disk divided by the mass of the disk. And if the angular momentum per particle is conserved, then this is 1. Okay, so that makes that as a very convenient little parameterization. Okay, finally, before lunch, we need an expression for this energy. And to do that, you have to write down what the binding energy is of the isothermal sphere and use just a simple expression for the total energy. I don't know why I closed this. Well, because I was going to have an intermezzo. Okay. So the energy is going to be the sum of the potential energy of the system plus the kinetic energy of the system. And the potential energy of the isothermal sphere you can calculate in the standard way, and that is minus R Vir and the kinetic energy is only m Vir V Vir squared over R over 2, half mv squared. So that's the standard form. This is in a slightly non-standard form because it's convenient to write it like that. And you can introduce here now, use that the V Vir squared is G m Vir over R Vir. You can put that in here. That cancels out nicely the R and the G here, and you'll end up with minus G m Vir squared divided by 2. That's just replacing V Vir with this expression and doing the same thing here. So now you see this is, sorry. Yeah. It doesn't look right to me. Oh yeah, no, that's right, sorry. Wait a second. Okay. I'm a bit confused here. Let's see. Okay, let me insert that into the expression now. Insert it in here. So the disk scale length is now going to be G m Vir 3/2. There's something wrong here because it doesn't. Oh, there's an R Vir missing here. Otherwise the units are not right. Sorry. When you make a mistake in the writing, it's somewhere it ends up like that. Okay, m Vir with 2 V Vir, 1 over square root of 2, because you do square root of this thing, m Vir 2.5. Okay. Now I see what I had done. Okay, sorry. I wrote these in various lines. It's indeed true. This should be an R there, but what I rewrote it as for convenience for myself was V Vir squared divided by 2. And that's easier when I wanted to put it in here. And then V Vir to the first power. Then that is, and then lambda, and then the JD over FD. So that's G m Vir over V Vir squared. That's what I wanted to have here. And then 1 over square root 2 lambda JD FD. And this is the virial radius, right? That's R Vir. And so what you finally get is 1 over square root of 2 virial radius lambda, and then JD over FD. And that's actually quite a remarkable thing. It tells you, if you give me a dark matter halo and you say what its spin parameter is and how big it is, I can tell you the size of the spiral galaxy that falls inside it. Conversely, I could take a spiral galaxy like the Milky Way, take its size, and I can make an estimate by saying, oh, it's probably in a typical dark matter halo. I can tell you what the size of the halo is. Or if I know the size of the halo, I can tell you the spin parameter. Or likewise, this has to do with the mass of the halo. So it basically says, given the mass of a halo, I can get your radius. And you can go even one step further, and you can say, oh, I actually know this press-Schechter mass function, which tells me number of halos with a given mass. I can actually take this, use this expression, and it will give me the number of spiral galaxies with a particular size. Just converting the virial mass, which is what goes into the press-Schechter function, solve this for the virial mass, as an expression of RD, and you can plug that into the press-Schechter function, and you will get a prediction of size distribution of spiral galaxies as a function of halo mass. And it actually works not too badly. It actually works well enough that you can use it as a first guess. And you can get quite close to the right answer. But it doesn't quite work. And the last thing before break is I'm going to show why it doesn't quite work. I don't know if maybe I have it on the slide. That would be quicker. So this slide here has this calculation, which I had sort of assumed that I would leave for you to fill out the blanks, but I think it's more instructive to go through and do it on the blackboard. But you can see the same calculations that go through here. Oh no, I didn't put it in. Okay, so that's the statements are correct. Let me just write down what it is for the Milky Way, just to give you an illustration. So the a bit too violent. Okay, back in action. Almost. Okay. So I just fill in some numbers, and I get that the disk size is about 10 h to minus 1 kpc jd fd lambda 0.05 VVIR 200 kilometers per second, omega m delta c 100 minus 1/2, and h of z h naught minus 1. Okay, and then there's a similar expression for the central surface density, which you can also get, which is 207 h to minus 1 solar masses per parsec squared times a bunch of different parameters that you can find in the lecture notes on the web page. I'm not going to write them all out because they're going to go until there. Now the Milky Way, the circular velocity is of the order of 220 kilometers a second, something like that. The total disk mass is probably of the order of 5 times 10 to the 10 solar masses. And the disk scale length, well, that's a bit more variable, but people tend to converge on something of the order of 3-4 kiloparsec. So say 3.5 kiloparsec. If you put that in, and you use these two equations, you can solve for lambda, and you can assume JD over FD equal to 1. So that means that angular momentum is conserved. There's no exchange of angular momentum between baryons and dark matter. If that's the case, then you can solve these two equations, and you will get that lambda is about 0.01, and FD is about 0.01. For the dark matter halo, well, this is for the dark matter halo of the Milky Way, and that's for the Milky Way disk, yeah. Exactly. And
Like 10%.
1%. Oh, yeah. Of the total mass, it's about 5%. Yeah, yeah. So, yeah. So if I go back here, I said the solution here says that the dark matter halo of the Milky Way should be about 0.01. That's here. That is only a couple of percent. 1 to 2% of the halos have a spin parameter of that. So that's not very nice, at least not in the Copernican principle that says that the Milky Way should be typical. Maybe it is atypical, but there's no other evidence that it is. So this is problematic. And the other problem is this fraction of 0.01. If you say that the halo is filled with baryons at the same level as the baryon fraction of the universe, which is about 20%, what this is saying is that only 5% of the baryons come into the disk of the Milky Way. And that sounds very, very low. People don't like that. It's very hard to make something like that happen. That's different from forming stars, remember? It just means that it comes into the halo, into the disk. 5%, that's very low. So that means that this methodology, it gives not crazy results. It does give you trends that are not unreasonable, but it fails in detail. And the solution to this is actually these two things. Firstly, the dark matter profile is not an isothermal sphere. So if you put in an NFW profile, you do the same calculation, exactly the same I did here, except you now have to do the integrals numerically, because you can't do them analytically. You'll find that the solution is a lot better, and if you in addition include the self-gravity of the disk, only in the simple way that it modifies the circular velocity curve, then you get results that agree much better with observation. The Milky Way halo is a typical halo, about lambda of about 0.35, 0.04, and FD of the order of 0.05 or so. So then you say that something like 30% of the baryons come into the disk. If you want to do better than that, then you need to simulate the individual bits and pieces of the disk, look at where stars form, what's the effect of feedback, etc., etc. And when people do that, and they have done that quite a bit, this is the simple solution, by the way. This is including NFW profile and self-gravity. This is observations of circular velocity size for a sample of spiral galaxies. And you can see that they fall within the reasonable predictions of this model. But there might be something slightly wrong with redshift evolution. But it's more or less getting the trends right. You can do a slightly better job. That's what, for instance, this work by Dutton and van den Bosch did. And now this is including feedback into the prescription. And now they can really, they predict that spirals should lie between these green lines here. And the observational data, which are the dots here, indeed, most of them lie within these green lines. So, but the fundamental physics that go into it is essentially what I covered here. It's just an exponential disk. Look at rotation of that exponential disk. Take into account the potential of dark matter, because that's going to control the dynamics. And you get basically this kind of prediction. And importantly, you get the relationship like this. RD is proportional to the virial radius and to its angular momentum, but there is a slight modification function here, which depends on the details of the dark matter potential. So that ends pretty much spot on the mark, this one. And I had now planned to finish reionization, but we will do that after lunch instead. So that will be the final bit, going back to the beginning. But this took a bit longer. This was planned to have covered this yesterday, but clearly that was a bit optimistic. So any questions about the spirals or things you want to ask about now, or do you want to ask about it? You can also ask after lunch when you've had time to think about it. But this is actually a very nice result, that you can get the disk sizes simply from knowing about the dark matter halos. It really is quite a remarkable and quite a simple result. And one of the few things you can do analytically in galaxy formation and get more or less the right answer. All right, I'll see you at 2 o'clock, I think.